So first of all, if you look at this should look really familiar here. Right? That's linear. So basically, that's the solution to conduction through a plane wall. Right? That's the linear solution. And that makes sense because if you take G dot here, right, this now then is the generation term. The generation term. So if you took that and you set G dot triple prime to 0, right, that whole term goes away and you're left with just your linear solution. So that makes sense, right? You want, in that case, for the solutions to line up. So that's good in that case that it works out. The other thing is to note that you get this sort of concave behavior, this parabolic behavior from this generation term. So any plane wall solution that involves generation is going to follow this profile. There's going to be a downward trending generation that's occurring, assuming G dot triple prime is a positive number. You're going to have this downward or concave trending generation term layered on top of the existing linear solution. Okay, so we can actually like plot that out or sketch that out. I told you sketching is important, so I'll do it too. Let's sketch out what it looks like for these different solutions, both in terms of the temperature profile, but also in terms of the heat flux. So let's start with maybe the baseline case. Let's take, so here we've got TC, here we've got TH. Hopefully you can see my blue all right. So on the left, we're going to say at TH. On the right, we're going to say at TC. We're going to hold those constant no matter what, right? Those are our boundary conditions. So let's first take a case where there's no generation, right? This is a plane wall solution. What does that look like? Right? It's a linear solution. We should be comfortable with that now. So this is where G dot triple prime equals 0. So now remember, I'm adding on, let me just kind of scroll back up a little here. I'm adding on this parabolic concave downward quadratic term. And as G dot triple prime goes up, that's going to become more and more dominant in the solution. So I can sketch out what that starts to look like. So let's say we have just some small amount of generation. Right? That might look something like this. Right? This would be the temperature profile. As you ramp up that generation more and more, it's going to look like this and like this. And so on, right? My drawing gets worse and worse. But this is what the temperature profile starts to look like. So this is kind of, I mean, it's interesting. It's, I don't know, like, you're like, maybe so what? But it's kind of cool to see maybe how it's going to respond. You can anticipate what's going to happen. Some things to note about this is, are that as you look at this solution, oops, sorry. Come back up, okay. So as you look at the solution, there's a certain point in the solution where heat is actually not flowing in any direction, right? Remember that heat flow, so think of it this way, heat always flows downhill, right? If you have a temperature curve, heat's always gonna flow downhill. So if we look at this, there's a crest to the hill. There's a particular spot where there's no heat transfer occurring at all. So in this solution, maybe that's right here. And this one maybe here, and this one maybe here, and so on. So as you start adding generation, you actually move this point where there's no heat flow closer and closer to just the middle, right? It's going to converge to the middle. So that's kind of interesting that there's this point. It also means that when you're adding generation, there's heat flow both in this direction and in this direction, right? So it's no longer just that, yeah, you're holding the left at TH and the right at TC. Doesn't mean that heat's always flowing just in one direction, right? It can be flowing in the reverse direction, right? So let's maybe sketch the Q dot part of this, because that's a little interesting too. So I'm going to draw a 0 line here just to set our baseline. So let's look at, like I said, there's a specific spot where heat is not flowing. So you're going to look for places where where the heat flux solution crosses 0, and it's going to change as a function of which generation you're looking at. It turns out if you actually go through and enforce these particular boundary conditions, there's a point where they all intersect. And that point for this solution happens to be at x over 2, or halfway through. Right? So at this point, all the solutions are going to intersect here. The other thing is, let's look back up here for a second before I actually sketch anything. So if I look back up here, and I look, let me just look this. So this one here, right? This is essentially what we're sketching. We're essentially sketching heat flux. So dt dx. What is the form of that equation? It's linear, right? So now our what previously was a linear temperature solution, by adding generation becomes a linear heat flux solution and a quadratic temperature solution. So if I go down and try to sketch this, I'll just kind of give you the end result here. You're going to see that you have a solution like this. So I could draw a straight line. You have a solution like this, like this, like this, and so on. Right, so this direction here is increasing heat flux, right, like this. Or this over here, on the left-hand side, this is increasing. Right, Q dot is increasing, or sorry, G dot is increasing. What I mean is not increasing heat flux, I mean increasing generation. Okay, got that clear? All right, so they all intersect at one point, and you start to see that the zero crossing line changes for the different solutions. Right? It's kind of a carrying it out to the conclusion there. Questions on this, and we'll do an example. Yep?
Will there ever be a downward slope graph, as in like there's no generation, or is that like stored? Or what does that look like if G dot triple prime is negative?
So if G dot triple prime is negative, like, yes, there definitely can be. So just you'd have to think of a process where there's negative generation, like freezing of ice, right? You are putting heat in, that heat is, you're taking heat out, and that there's a conversion of chemical energy into like freezing, right? I'm not saying that very well, but yeah, there are processes where it like goes backwards.